Welcome to another HVAC Engineering-Techie channel video. Today's lesson is on water-cooled central plant control system sequences. So basically this is sequences. These are pretty simple sequences for like hydronic heat pumps or water-cooled equipment. Something that takes a central plant for water treatment, or for a central plant for cooling. So remember, this is the channel that talks all things HVAC, engineering design, construction, equipment, systems, test and balance, controls, and efficiency and performance. So this is C-6 of our control series. Hope you've taken the previous ones to kind of get a little bit of background on controls, and this one will start our sequence. This is the simple sequence one. The others get more and more complex as we go along. And my purpose on these was to actually provide you basics for complex sequences. And I've been using ASHRAE Guideline 36 as our guide, and that's a very complicated reset sequences under Guideline 36. And hopefully I've simplified it for you and given you the basic standards to make those work. As a commissioner, sequences were always the hardest part of this job, getting the correct sequences, and hopefully these training videos will help you. Remember, before we start, I'd like you to become a subscribing member. If you haven't already, many of you haven't, I really appreciate that. To be a subscribing member, just hit the subscribe button down below. Give me a thumbs up if you like the videos. It's painless for you. It doesn't cost you anything, but Google uses those to judge these videos, which keeps me on the air. So I'd really appreciate it. So let's get started on C6, water-cooled central plant equipment sequences. So now we'll just kind of go through the videos again to let you know what videos we have in our control training series, in case this is the first video you're taking. C1 is the control system basics. You should take this just to make sure you've got all the language down and you know what all the acronyms mean. C2, DDC controller network devices. What are the different devices? DDC control architecture is an important one that you at least know what the architectures are. C4 is DDC control components and devices. 5 is control wiring and installation, and this is C6, and this is about the general sequences for water-cooled equipment central plants. So if you have water-cooled air conditioners that take a central plant, this would be the sequence of controls. C7 is hot water central plants. C8 is chill water central plants. C9 is constant volume air handler control sequences. C10 is VAV air handler control sequences. And C11 is outside air handler control sequences. C12 is loop tuning, which is really important. C13, how to select and size control valves. C14, how to size and select control dampers. And C15 is HVAC pneumatic controls. We no longer do things completely with pneumatics, but we still use a lot of pneumatics in certain systems that have overlays, and that will be explained in that session. So let's go ahead and look at HVAC control sequences. The main technical resource used in this presentation is ASHRAE Guideline 36, 2024. High-performance sequences of operations for HVAC systems also utilize the standard industry practices. Now, this particular training session for water-cooled equipment, the sequences are much simpler, and we don't have a lot of double resets. That's where Guideline 36 really helps us to understand how to keep the system's working correctly for when you have double resets going on at the same time. This one, we don't have any double resets. But we still use some items from 36, but not the depth we will in the other sessions. Normally, the design engineer describes their desired sequence of operation in standard language on the drawings or in the project specifications. So the engineer, he writes a sequence in English of explaining what he wants his system to do. Now, that's what we need from him because we want to know how he wants it to operate, but to program it and to commission it, we need a lot more detail. We need to have timers in there. We need to have exit points in there and entrance points, and the engineer is not expected to be able to put those in there, but we need to see those. So that is why we look at sequences in detail. Now, possible issues with the sequences, new innovative sequences that's never been used before. Some engineers are really smart people, and they get into this boat of inventing a new innovative sequence that no one's ever seen and maybe has never tried to use before, so it becomes very complicated to program, very complicated to test, and almost impossible for operators to operate the building. So we try not to have innovative sequences there's pretty much a sequence for everything you can imagine that's been out there, tried and tested. Maybe not. You invent a new system, you might have a new sequence. But what I tell an engineer is if you're going to do this, if you're going to invent something new no one's ever seen before, you need to put enough money in your project to be able to train everybody that needs to be trained, which is the contractors, the control contractor, the test and balance contractor, the commissioner, and the operators. All exactly how the system's supposed to work. And then because you've invented something new, you're liable for anything that doesn't work. So you need to be really careful about what you're doing, that you don't have any open-ended problems. It could be incorrect logic, or logic components of the sequence are not correct. And this happens all the time. It's not because they're not smart people or we're not smart people. It's because that when you're dealing with temperature and flow and pressures, you need to understand those are all connected in physics. And we forget about that. We deal with what we're doing, and we want to just reset the temperature. We don't realize if we have variable flow, then that changes the flow requirement. If you change the temperature, if you change the flow requirement, you change the temperature requirement. So it's important that we make room for physics. If we forget about it, it's going to get us. So that's why we need to make sure the logic components are correct. Too complex for successful implementation. I've seen some sequences from some young engineers that are so complex that a programmer it would take him months to figure out how to write the sequence. And then it would be full of errors because it's just impossible to write a complex sequence without having issues you haven't figured out before. So we really want to keep the sequences as simple as possible to do the job that the engineer wants it to do. Complex sequences are a disaster for everybody, including the operators. If you make a sequence so complicated that an operator can't deal with it, the system's never going to stay working. So we need to have simple sequences. Okay, so the way this is supposed to work is the engineer puts a sequence in English on the drawings or in the specification. The control contractor is supposed to take that sequence and rewrite it with the detail that he needs in it. Put all the timers in it, all the set points, all the entrance and exit points in that sequence, so it's what he's going to actually write. Now, we as a commissioner can look at that and say, okay, now we know what he's going to do. But that's not unfortunately what happens. What normally happens is the control contractor simply cuts and pastes the engineer's sequence on his submittal and says, that's what I'm going to do. Now, the control programmer and I also know that's not what he's going to do. He's going to have to add a bunch of stuff into that. And if you don't expose that, then you won't know exactly what he's doing, and you may not know how to test it, or you won't be able to identify if a test passes or fails. So what happens when we have that kind of situation where I know they've cut and pasted it, and they do that, not to save time, they do that so they won't get disapproved. If they change that sequence to what they're actually going to write, the engineer may just say their submittal's not good, it's not doing my sequence. But the truth is, what we'd really like to have them do is to have a standard sequence, or a sequence that's been written by the manufacturer and fully vetted and tested over many projects. That's the sequence I'd like to use because I know it's a good sequence. If we have a new sequence, then we're going to have to test and vet it in the field. So we want it as simple as possible and as complete as possible. Okay, what kind of the components of a standard sequence for water-cooled equipment? One, we got operating schedules. We know when the building's occupied. We know when it's unoccupied. We know what a start time and end time is, same for unoccupied. Space and variable set points for occupied and unoccupied conditions. Room set point dead bands, 1 to 3 degrees. Now, some lead requirements ask for 4-degree dead band, and that's not good. Because 1 degree, as a human being, you really can't feel 1 degree. You think you can, or you try to pretend you can, but in reality, you cannot tell the difference between 1 degree, pretty much. But 4 degrees, everyone can tell the difference. So if you use a 4-degree dead band, everybody's going to be unhappy about their space because it's going to get too hot before the air conditioning turns on. Then it'll get too cold, and it'll get too hot. It's not, at 4 degrees is too much. So I 1 to 2 degrees is what I would prefer, to keep the cooling and heating bands apart, but not 4 degrees. These are the standard temperatures out of Guideline 36. So occupied spaces for cooling are 75, 50% relative humidity. Heating is 70 degrees, 35% relative humidity. And the reason this is lower is because it costs a lot of money to put humidity in a building. In air conditioning, when we take the water out of a coil, we automatically have high humidity. So it's normally right off the coil, we're right around 50, 49, 48%. So 50% is easy for air conditioning. Depends. I mean, if you've got a size like me in the middle of the desert and you've got a lot of sensible heat, you may be down at 30%, but relative, that's what it is. Mechanical electrical rooms are 85, 65, and floating for relative humidity. We don't care. Operating rooms are 65%, 50% both for heating and cooling. Some operating rooms may have a control feature that allows them to keep it at 65 degrees and then run it up to 85 degrees as soon as they're done with the operation. Because 65 degrees, the human body responds best to what they're doing. And as soon as it's all patched up, they want it warm for them to come up out of anesthesia and all that stuff. Data rooms are 75, 35 both. Now, there is some changes out there. This used to be 72 degrees, but they've learned that they don't need that cold a temperature at the servers. So they can have up to 90, 95 degrees. So this could maybe actually even go to 80 degrees, but 75 is good, even 78. But the standard right now is 75 degrees. Unoccupied is for cooling is 90. Heating is 60. 90 to me is a little high for setback temperature. I like 85 better, but it's, these are all settable by you, or the operator can choose whatever these are supposed to be. The only thing about temperatures and humidity set points is you should encourage the operators to have it common throughout the building. So in other words, don't have one zone that has 72 degrees, the next zone has 78 degrees. Because any interaction of temperature is going to cost you energy. The same with humidity, it may be even worse. So you don't want to be putting it in one place and taking it out another place. That's just wasting energy. So you want to have it the same. I've always liked to see operators have policies that says our set points are 75 or 78 degrees, and that's it. If you want it to be 60, you're not going to happen. It's going to be 78. That's our standard across the building. Then the other thing here is standard default water temperature set points. Now, everywhere in these sequences we talk about set points or enter points or exit points. Everything is variable and can be set and limited by an operator. And there's reasons for that. If you get out there in the system, you may discover that your set points are so close you have cycling. So you may be spread a little bit to not have that cycling. So there's things like that that are always adjustable, but they have to make sense, what comes in the right order. But as far as their width, you can change those. So for condenser water systems, which we'll be dealing with in this session, cooling is 85 and heating is 75. Now, the one good thing about these is water-cooled equipment is really forgiving about temperature. It has a wide band. Mainly a lot of systems are very close band, maybe 10 degrees band or 20 degrees band. Well, in condenser water, we can be a lot bigger. We can go clear up to 105 degrees and down to 65 degrees, so we can have a big band. But these are the center points, the set points that we want to use. And unoccupied can go to 95, 65 because we don't anticipate units to be running when the building's unoccupied. It might once in a while, so we have set points for that. Chill water is 44, heating water is 130. But we're not going to be dealing with chill water and hot water in this session, only condenser water systems. Control sequence standard components. Okay, start, stop, the conditions for startup, sequence condition for shutdown, what happens before we start up, what happens before we shut down, optimal start conditions. Now, controls have possibility of having an optimal start and optimal stop. What that means is an optimal start, the system remembers how long it takes to get from night setback to occupied set points, and then it will use that time to set it. So you say, I want optimal start, and I want to be at 75 degrees at 6:30 in the morning. That unit will start it up however soon it has to be at set point start time. It's very good. It saves a lot of energy, because before this, people just said, we're going to turn it on an hour early. Even though there's no one in the building, that's not productive, and you don't need to be burning that energy. So we'll do optimal start. Optimal stop is similar. The system remembers how long it takes to get out of temperature range, so it'll turn the system off early. We don't use that one very much because the air conditioning systems put white noise into the building, and if you shut it off early, everyone will know how noisy it is, and then it'll like that. So We don't use stop. We just let it run and we stop it when the building goes out of occupancy. Because of that factor, people all say, it's really noisy in my building. Well, how do you know? Well, when it shuts down at night, I can hear how quiet it is with that, and I like that. So we don't use optimal stop very often. Condenser water temperature control, that obviously we do. Temperature control sequence for both cooling and heating. Temperature control reset sequence, if it's going to be reset. Condenser water pressure control, we don't normally do pressure control, but you can. Supply a pressure control sequence or supply water pressure control sequence reset. Don't use that very often, but you could. Operational trend data for the operators, sensor data, runtime, and operational alarms. So all of these things need to be in the sequence. Now, engineers don't normally put optional alarms and don't put data trends, but we need the control contractor to build those for the operator so the building's ready to operate when it's turned over to him. Most important items for energy reduction. Condenser water set points. That's really important. Condenser water set point resets. If it's got resets, we want to maintain those resets. Loop tuning. All output loops fully commissioned and tuned. Now, that's a special process how you tune loops. These are analog loops, of course. And we have a training session for that, of course. And the control contractor needs to tune those loops, and the commissioner needs to be verified that they're tuned. And this is how we do that during our functional testing. Occupancy schedule strictly maintained. So in other words, what happens a lot of times is a customer will have a problem, and an operator can't figure out what's wrong and how to deal with it, so he just blows out the schedule and let the system run 24 hours. So the next morning, that customer will be comfortable, but that just costs you a whole bunch of energy because, if you have like this, a water-cooled system, and you want to keep one heat pump running, you have to keep the whole central plant running. So that's not an option. We should never do this. We should figure out what's wrong, find the problem, and fix it instead of trying to blow out a schedule. Sometimes they'll blow out a temperature reset schedule. We're just going to dive that condenser water down to 75 degrees, and we'll make these units work right. But at what cost? It's a high cost, so you don't want to do that. Operations committed to maintain operations of the above. So the operators have to keep this. We need the system to maintain itself, to keep running correctly, to be able to the right energy usage. So that's an operator commitment they have to make. So here's a water-cooled package system. So these are standard AC units that have condenser bundles in them to condense the heat away from the units. And we use pumps to pump water around for that, and we use a fluid cooler. It's a cooling tower, but it's a fluid cooler. And a fluid cooler has a heat exchanger inside here. And this water runs through that heat exchanger and through these heat exchanger bundles, so it's a closed loop, right? And then we have this fluid cooler, which has a water basin in it. It has a pump. So when we need cooling, it turns on this pump and pumps water over the top of this heat exchanger to cool the heat exchanger. And then it has a fan up here that comes on to force draft through that heat exchanger and water to provide much more cooling. So that's a fluid cooler. So we have more control points because we have to run this pump and this fan. And here's a point list for that. So the point list is we have a digital output for P1 pump. We have a digital output for P2 to start those pumps. We have a DO3 for the cooling tower pump, this pump to run this fluid cooler. And then we have a VFD to run this cooling tower fan, start-stop. Now, the reason I put VFDs on these, you could put just a starter on them. But over the years, I've discovered that every cooling tower fan, fluid cooler fan, or refrigerated fan needs to be on a VFD. It just works out that the condensing temperature is always fluctuating, so the fan is always going to be modulating, not at full speed. And it will save you energy. It pays back in less than 18 months, every one I've ever calculated. I got to where I just gave up calculating because it's just a good deal. Not only does it save you energy, but it protects the gear drive or the belt drive on the fans because the VFD starts slow. It's a ramp start, so it's a very good motor minder and takes care of it. Analog outputs is this VFD for this fan speed, so we have an analog output for that. We have digital inputs, D1 for the starter status for P1, starter for P2. We have D3, a starter current. We look at the VFD of a current with a starter to make sure that's running correctly. And we have coming off the VFD fan status that the fan is operable on the fluid cooler. And then we have analog inputs. We have a temperature sensor for the condenser water supply temperature and the condenser water return temperature. We have an outside air temperature and an outside air humidity temperature. Now, these two may be coming in from global points, but we need to have those. So if they're coming in at global points, they don't burn points on a controller. They just come into the software. But if we don't, we have to have them out there. And many times in the central plant is where the outside air temperature and outside humidity sensors are that broadcast to the rest of the system. AI5 is the VFD speed percentage, what speed are we actually running. And then if you want to make this variable flow on these system pumps, see, I have them constant flow with starters. You can do that. What you do to do that is you have to come out here and you have to put valves, automatic valves on these AC units. So when they're off, that valve is closed. But when it's on, it opens that valve. And that allows flow. So if these two have no flow and this one has flow, and then this one comes on, these two have flow, this have no flow, you can see that's variable flow, right? It runs a variable flow. So what you do is you put a pressure sensor 2/3 of the way down here, and you maintain whatever the PSI delta you need for that, and it'll variable speed these pumps. To do that, you would put a VFD here and a VFD here, so you'd have VFDs on these pumps. You have a speed, and then you have an optimal speed control. Here's the condenser water D-piece differential pressure sensor, which would be out here. So you have to add this point, and then you, if you do have these points now become optional to the VFD. Now you can also do a net connection here, so you can run a network to a VFD, and you can suck up all its points. I mean, they may have 20, 30 points that you can suck up. However, you should always have at least one hardwired start-stop to a device, and that's in case if you have a burp on the network. I mean, you might have, something network. Maybe the IT guy takes the network down to work on it, and all of a sudden you can't turn it on and off. That's a bad deal. So you want to rely on network to gather a lot of data and give you stuff that you can use. It's interesting, but it's not critical. Otherwise, if it's critical, like speed control, I always put hardwired points, and if they want net connection, we'll bring in a network connection on top of it. Those are the points for a water-cooled package system. All right, let's look at the sequence. Schedule. The system shall be enabled and disabled based upon an occupancy schedule. When do we normally want this building scheduled? Now, you can also do an optional schedule, and that is have the system turn itself on. So you can do that by watching when a heat pump comes in. If all the heat pumps are unoccupied, they're off, so the central plant's off. One becomes occupied for whatever reason, becomes occupied. This valve opens, and then it sends a signal to the central plant to start. And so then the differential pressure sensor starts these fans. So this all starts and can run that unit. Now, there's a deal very important here, is that you never allow the heat pumps to run unless this is flowing water. Because if you start these heat pumps before you flow water, these will go off on a high head, and they have to be manually reset. Now, normally they power cycle them to reset them, but unfortunately on most buildings it's very difficult to just power reset the AC units. The owner won't like you resetting the whole building, but you might, but normally you have to go do these one at a time. It's really a pain. You don't want to do that. So basically this system runs the AC units. When they run, it turns on the central plant. When they're all off, the central plant goes down. It does that by isolation valve is open and the lead pump shall start. Once flow is proved, the AC unit should be enabled to run. When no AC unit is in the occupied mode, the system shall shut down and enter the unoccupied mode. So you can use this as a optional schedule to a hard schedule. But a hard schedule works too. It just says that if no one pushes an override button, now on a hard schedule, if you have override buttons, then you have that switch the central plant to occupied mode is all. Pump lead lab status, since we've got stage pumps, one handles the systems, one's a standby. Lead lag status of all pumps shall be based upon operator selection or rotated automatically every 7 days. If any pump fails during operation, it shall be locked out of rotation and until repaired and placed back into rotation scheduled by an operator. So in other words, an operator needs to say this pump's ready to run before it places it back in rotation. System pumps. These are the system pumps. Start the lead pump when in the occupied mode. If after 5 minutes the lead pump current switch status points indicates no flow, then start the lag pump and alarm pump failure. Once flow is confirmed, enable all connected AC units to automatic run control. Now, you can run variable speed pumps like I mentioned, and this is that each AC unit has an automatic isolation valve that opens when the AC unit runs. The system pump shall modulate speed to maintain the condenser water differential pressure set point of 15 psi or whatever is established by the tab contractor. If the pump speed drops below 15 hertz for more than 15 minutes, or maybe 12 hertz, that's all adjustable, but you can't go too low because the motor windings need cooling, and the fan of the motor provides that cooling, unless you have a true VFD motor that has a separate motor for cooling, and most of them don't. So you can't go to zero. You can't go off because you'll heat up the windings and it'll burn the motor out. AC valves are closed. If more than 15 minutes, it's down at 12 to 15 hertz. Then and all the AC valves are closed, then stop the system. Restart the system pump if any AC valves open for more than 15 minutes. Now, these timers give us some flack so we don't short cycle any system. So it takes 15 minutes, then it'll come on. That way, its temperature's heated up a little bit. It'll have a little bit more load for that time. Cooling control. If the condenser water temperature is above 85 degrees for more than 15 minutes, start the fluid cooler pump. If the condenser water is above 86 for more than 3 minutes, start the cooling tower fan. Maintain the condenser water temperature set point of 85 degrees by modulating the fan speed between 84 and 86 degrees. Stop the fan if the condenser water drops below 83 degrees for more than 3 minutes. Stop the fluid cooler pump if the condenser water drops below 82 degrees for more than 30 minutes. So you'll see this is the sequence. So if the water gets to 83 degrees, 85 degrees, then it turns on the pump, turns on this pump, the fluid cooler pump, turns it on. But if it gets below 82, it turns it off. And if the temperature gets to 86 degrees, gets up to 86 degrees, it'll turn the fan on. And if it gets below 82, 83, it'll turn it off. But while it's on, it will modulate depending upon the temperature between 60 hertz and 12 hertz, which is minimum. I mean, you probably could go to 10 hertz, but not much lower than that. So this is the speed. It's going to write the speed up and down, trying to maintain this 85 degree temperature set point. So if it's over it, it'll go full speed. If it's under it, it'll go below. This is just a temperature cooling diagram. Monitor points and alarms. Monitor all temperature sensors. If the condenser water supply temperature is above or below a set point by more than 5 degrees for more than 15 minutes, send a level 3 trouble alarm. Now, level 3 is a trouble alarm that an operator says, okay, I got a problem. I need to look at that when I get a chance. It's not immediate, but he should know that it's there. A level 2 alarm is an alarm he needs to get up out of the chair and go do something because it needs it too. A level 1 is the life safety, and a level 1 alarm should have gongs and alarms going off everywhere, and everybody needs to be concerned about a level 1. But level 3 is a trouble alarm that we need to check. And level 4 is some kind of status alarm that doesn't matter much. That you just want to log it, but you don't really need to get out of your chair. Alarm all equipment run failures at a level 2 alarm. So if something fails, level 2, you need to go check what's going on. Data trend condenser water supply and condenser water return temperature continuously with an interval of 15 minutes. So every 15 minutes, we're going to data log a data trend of where the supply and return is on this condenser water. So an operator can bring that up and look and say, well, here's what we're doing. We're doing pretty good. Or, boy, something's going wrong. We need to check this out. So since it's every 15 minutes, it's only 4 points an hour. So it doesn't take a lot of data, but it does show you what's been going on. Data trend, now, if you need a real close diagnostics, you need to set up a trend a lot closer time than 15 minutes. But for an operator continuous trend, 15 minutes is fine. Data trend outside air temperature humidity, the same, every 15 minutes. Data log runtime of all motors. So we're going to just keep track of the runtime of motors so the operator can see that, and it's resettable by the operator in case he has to change a motor. So if he changes a motor, he needs to reset the time back to 0 hours. Now we have heat pumps. Now, heat pumps are exactly the same as what we just looked at. It's got water-cooled heat pumps with heat exchangers in them, And we have pumps and we have a fluid cooler, but now, since these are heating, we need to have a boiler. In case it gets cold enough that these suck all the temperature out of the water, we'll need to add some temperature into it. So you can see the point list is longer. We have more points for this. Now, the way the heat pumps are a fairly efficient system, hydronic heat pumps. So what makes them efficient is one can be in cooling and one can be in heating, and they can actually trade that temperature back and forth, so they don't need to go through and make temperature here or make temperature here, because this may be acting like a boiler. If it's in cooling, it'll be adding heat. If this is in heating mode, it'll try to draw heat out of the pipe, and that transfer of heat between the units is what makes them efficient. So you don't need to make it every time. You can get it. So the point list here is start-stop of P1, P2, which are starters for these systems. We have a isolation valve now. We have automatic isolation valve on the fluid coolers. So we can take this out. What happens is we don't want this fluid cooler in operation during the cold winter months. Because if you did, what would happen is this boiler would put heat in the water, and when it went through the pumps and ran back through the fluid cooler, it'd be evaporating heat out of the top of this cooling tower. You'd be throwing away tons of heat, and you don't want to do that. So we put an isolation valve to close it down. So then we have these isolation valves. We have a starter for the cooling tower pump, this pump here. We have a VFD in the cooling tower fan, again, just like the other one. We have a boiler primary pump start. So now in the boiler, we've got a primary pump to run water through the boiler. And we have the boiler enable disable. And the reasons for this is because we use side stream boilers. So the full flow of this does not run through the boiler. And the reason is boilers need to have a minimum, at least water tube boilers need to have a minimum discharge temperature so that we don't condense on the boiler tubes. So what happens is you may have 100 GPM running through here, and you may only have 30 GPM go through the boiler, and it may exit the boiler to 130 degrees. This will be balanced, so when it's on, this boiler can take cold water and leave it at 130 degrees, and then it mixes with the water here because this is a side stream boiler. So this may get it up to 75 degrees. If this is 60 degree water, comes down, this little bit of water comes in and leaves it at 135 degrees, and this 135 degree water mixes with the 65 degree water, providing us the set point we want. So that's why we do that way. The analog output is the cooling tower fan speed control, just like the other one. A digital inputs is a current switch on P1 and P2 to tell if they're actually running loaded. A D3 is a valve position, so we have position switches on these. Condenser current switch on the pump status on this one to make sure it's running. VFD on the fan status. We're doing fan status off the VFD. Current switch on the primary pump status, which is this primary pump in the boiler. And then we have a boiler. We start and stop this boiler in the panel. Now the boiler has its own internal temperature controls. All we do is enable the boiler or disable the boiler and let it run. Analog inputs are temperature sensor for condenser water supply, a temperature sensor for condenser water return, outside air temperature and outside humidity again, and then temperature sensor of the leaving boiler temperature. So we have a temperature sensor up here just for the leaving boiler temperature. And we have a EFD speed percentage to know what speed our cooling tower is running. And then if we want this variable flow again, we go over here and put valves and then put VFDs here, and then we'd have to put a pressure sensor just like the other one if we wanted variable speed. We could do that by putting these valves out here. Same thing as the other. And then these are optimal points. If we have variable speed, we want VFDs on those. We can put a net connection on this VFD, and then we can net connection all the VFDs. All right, sequence. The system should be enabled and disabled based upon an occupancy schedule, just like the other one. Same, we can have this schedule option. We can have the system start the system just like the other one. So the system shall be enabled and disabled based upon an occupancy status of each heat pump unit. When any heat pump is in the occupied mode and the isolation valve is open to the heat pump, the lead pump shall start. Once flow is proven, the heat pump unit shall be enabled to run. When no heat pump is on and the unit is off, she'll shut down and enter the unoccupied mode. So if this is in the unoccupied and they're all off, and one comes on and this valve opens, then it sends a signal to the central plant to start. The central plant starts and proves flow, and then it unlocks this unit and allows the compressor to run. Can't run it unless this has flow in Pump lead lag status of all pumps should be based upon operator selection or rotated automatically every 7 days. If any pump fails during operation, it should be locked out of rotation until repaired and placed back into rotation by an operator. It's really important that someone fix a pump before we try to run it again. System pumps, that's these pumps here. This is now system pumps, and these are now a primary pump over here. Start the lead pump when in the occupied mode. If after 5 minutes the lead pump current switch status point indicates no flow, then start the lag pump and alarm lead pump failure. Once flow is confirmed, enable all connected AC units to start automatic run control. Here's the pump speed one if you want to do that. Each heat pump has an automatic isolation valve that opens when the heat pump unit runs. The system pump shall modulate speed to maintain the condenser water differential pressure set point of 15 psi or whatever is established by the tab contractor. If the pump speed drops below 15 hertz or maybe 12 hertz for more than 15 minutes or all heat pump valves are closed, stop the system pump. Reset the system pump if any heat pump valve opens for more than 15 minutes. So this allows this system to run the central plant, but also it runs at variable speed. All right, cooling control. The condenser water supply is above 85 degrees for more than 15 minutes. Open the cooling tower isolation valve and close the cooling tower bypass valve. If the condenser water is above 85 degrees for more than 3 minutes, start the fluid cooler pump. If the condenser water is above 87 degrees for more than 3 minutes, start the cooling tower fan. Maintain the condenser water supply temperature set point of 85 degrees by modulating the fan speed between 84 and 86. Stop the fan if the condenser water temperature drops below 83 degrees for more than 3 minutes. Stop the fluid cooler pump if the condenser water drops below 83 degrees for more than 5 minutes. So here's the deal. So we have, if you look at this, if the condenser water is cold and it keeps heating up, and it gets to 85 degrees, and this cooling tower pump comes on, and we start circulating water through the cooling tower, which will start to provide a little cooling effect on the heat exchanger. Not a lot, but a little bit. So if the temperature continues to rise and it gets to 86 degrees, then we enable the cooling tower fan, and it starts to run. When it's on, it will ramp from minimum 12 hertz, clear up to maximum 60 hertz, depending on the water temperature from 84 to 86. And it does that to maintain 85 degrees. So it will modulate up and down until the temperature gets below 83 degrees, and then it will shut the fan off. Remember that VFDs have this minimum speed because the fan that cools the windings is on the shaft of the motor. So you can't take the motor to 0 speed because it'll burn the motor, unless you have a true VFD motor, which has a separate motor and cooling fan. I've actually never seen one. I know they make them, but they're really expensive, so no one buys them. So for a motor, you can't take it to 0 speed. Now, I've had some control contractors say, there's no problem, we do it all the time. Well, you shouldn't do it all the time because you can damage a motor. So we need a minute. So what means we need to turn it on and off. Running speed doesn't turn it on. You have to have a separate start-stop point and a separate speed point. So when it's running down a minimal speed, from 84 to 83 degrees, it gets below 83, it turns it off. So now the fan is off. And so then if it continues to drop and gets below 82, then it turns the pump off. Then everything goes dormant. Then the central plant's in unoccupied mode. Boiler control. If the condenser water supply is less than 80 degrees for more than 30 minutes, open the cooling tower bypass valve and close the cooling tower isolation valve. Start the boiler and primary pump if the condenser water drops below 72 for more than 3 minutes. The internal boiler fire control shall maintain the boiler leaving temperature set point of 130 degrees. The system set point during boiler operation is 75 degrees. Stop the boiler and primary pump till the condenser water temperature rises above 78 degrees for more than 15 minutes. So you realize that these set points are separated by these cooling set points, so we got a dead band between heating and cooling. So up here in this cooling tower, we have this valve and this valve. This is an isolation valve, and this is a bypass valve. So when we're in cooling, we shut this valve and force all the water through the cooling tower, and we open that valve. So this valve is open, this valve is closed, so all the water goes through the fluid cooler and out. During heating mode, we want this valve closed and this valve open, so all the water bypasses the cooling tower, so it's not letting the heat get out of it. and then we side stream to the boiler. So the hot water goes to the units, and it comes back, goes to the pumps, and comes right back and just to the boiler heating the water up. We don't have the fluid cooler in the mix. So here's its temperature. If the temperature gets to 72 degrees, it turns the boiler, enables the boiler. The boiler comes on to fire, and it will adjust. The boiler fire control will control it, trying to maintain 75 degrees. If it gets above 78 degrees, then it will turn the boiler off. It'll disable the boiler. And this is a real simple boiler control. Remember that we're trying to keep away from these temperatures of 83 to 86. And here we're 81 to 69. So there's a difference in those temperature ranges. Now remember, all these ranges I've given you are all changeable. This is just my recommendations, but you could tighten these up or lengthen them out depending on whatever you wanted to operate. And of course, it has to be within a range that the heat pumps can actually use the water. And 72 is fine, and this 87 is fine. If you think about it, it's just like a package air conditioning unit outside, and the outside temperature is 87 degrees. It's all cotton, right? That's an easy place for it to be. So water-cooled provides high energy efficiency because the condensing temperatures are reasonable. The monitor points monitor all temperature sensors. If the condensed water set point is above or below set point for more than 5 degrees for more than 15 minutes, send that level 3 trouble alarm. Alarm all equipment run failures. That'll run 2. If a boiler fails, got to be a level 2. Data trend, condensed water supply return temperatures every 15 minutes. Data trend outside air temperature emitted continuous with an interval of 15 minutes. Data log run times of all motors, and it's all resettable by maintenance when they fix a motor. So now let's look at a different system. And this is a system that we don't see a lot, but the reason this system is popular is because it uses a standard cooling tower, not a fluid cooler. And the reason for that is the fluid cooler or cooling tower is the most vulnerable part of the system. The water is very corrosive, and the fluid cooler or cooling tower is the first thing that will degrade and have to be replaced. Well, the fluid cooler, because it has that large steel heat exchanger, it's very expensive. So, and it also takes more power to run the air through that heat exchanger. So they're not very energy efficient, and they're really expensive to place. So what we came up with is an alternative is we bought a flat plate heat exchanger, installed a second set of pumps, and use a standard cooling tower. And what we do is we run these pumps, and we run the cooling tower water through the heat exchanger. And these are cleanable, of course. And then we have this several system just like the others, whether it might have a boiler downstream or not. But this is the system they support. So it may not be intuitive, but the cost of this heat exchanger and the cost of these pumps and the cost of that cooling tower are just slightly higher than the cost of one fluid cooler. But if you have to change the fluid cooler every 10 years, this is, this cooling tower here on a 100-ton system might be $5,000. A 100-ton fluid cooler might be $25,000. So it could be a huge difference. So this was very popular because I could reduce the energy consumption of the system by 30%. It's a large saving in energy, and this paid for itself very quickly. So what happens is we just use a standard cooling tower, and we'll go through that to look about it. So standard cooling tower, heat exchanger. So here's the point list. DO1 is this pump start-stop. DO2 is this pump start-stop. DO3 is this pump start-stop. DO4 is this pump start-stop. DO5 is the cooling tower fan start-stop. Analog outputs are the VFD cooling tower fan speed. And we made this one here. This is assuming that these pumps are variable speed. They don't have to be, but they can be. So if this has valves on the equipment out here and has that differential pressure sensor, then these can be variable speed, and I left that this way. Digital inputs, VFD pump 1, VF2 status. These two are VFD statuses. P3 pump status, these are just starters. P4 is a starter, and VT DI5 4 is the fan status off the VFD, off the fluid cooler. Analog inputs, condenser water supply, condenser water return temperatures. Condenser, so now we have temperature sensors here, and we have temperature sensors here. So we have temperature sensors here for the system, and we have temperature sensors here for the cooling tower. So we have that analog input 1, condenser supply temperature, condenser water return temperature, which is these out here. Then we have a cooling tower condenser supply, cooling tower condenser water, which is these two here. And then we have outside air temperature, outside air humidity. We have the VFD speed off the fan, and we have a differential pressure sensor out of the system to run these VFDs. So that's the standard for that. Let's look at the sequences. Again, we have a schedule. Systems to be enabled and disabled based upon an occupancy schedule. Pump lead lag, same thing. We're going to lead lag the pumps if one fails. We're going to start the lag pump and alarm that we have a pump failure, and those are going to be locked out until they're fixed and put back in operation by an operator. System pumps start the lead pumps when it's occupied mode. If after 5 minutes the pump current switch status point indicates no flow, then start the lag pump and alarm the lead pump failure. Once flow is confirmed, enable the AC units. That applies to these pumps, and it applies to these pumps, but they'd be on a VFD. So instead of a current switch, it'd be a VFD telling you that it's not running. Cooling tower pumps. If the system, that's these pumps here, the cooling is above 85 degrees more than 15 minutes, start the cooling tower lead pump in the cocky mode. And after 5 minutes, the lead pump current switch status point indicates no flow, then alarm. Okay. For cooling control, if the system condenser water is above 90 degrees for more than 3 minutes, start the cooling tower fan. Maintain and modulate the cooling tower fan speed to control the cooling tower water temperature using a PID control loop between 12 hertz and maximum speed at 83 degrees and 87 degrees. If the cooling tower fan runs at minimum speed for more than 15 minutes, stop the fan. Now, note that due to the heat exchanger approach temperatures of 5 degrees, the heat exchanger leaving temperatures will be 87 to 91 for the sequence above. So what that says is these here are the system pumps. This is the variable speed. We're assuming that we have variable speed on the system pumps, so we have valves on the heat pumps down out here. And the cooling tower fan will run from 83 to 87 degrees, trying to maintain 85 degrees. But we have a 5-degree approach temperature between the heat exchanger and the cooling tower fan. So these are going to be 5 degrees, and normally that's a 2-degree heat exchanger and a 3-degree cooling tower, or something in between there. And you'll have, instead of having 85 degrees here, you'll have 89 degrees here. So we're trying to maintain that temperature. Now these can all be lower as long as you have ambient loads that allow a colder temperature. 85 degrees is just a standard temperature, but the heat pump system or a air-cooled or water-cooled system will run down at 75 degrees, no problem, or 80 degrees. So if you have colder temperatures, say it's not the hottest part of the year, you can drop these down and have it run colder temperature. It just runs the fan a little longer. So I've set these the highest that would be amenable, but you could actually set these lower. Motor points, trends, and alarms. Monitor all temperature sensors. Condenser water temperatures above or below set point by more than 5 degrees for 15 minutes. Sends a level 3 trouble alarm. Alarm all equipment run failures, level 2 alarm. Data trend, condenser water supply, condenser water return temperature continuously with an interval of 15 minutes. Data trend, the cooling tower water supply and the cooling tower water return temperatures every 15 minutes. Data trend, the cooling tower fan speed continuously with an interval of 15 minutes. Data trend, outside air and temperature and humidity with an interval of 15 minutes. Data log run times of all motors assemblies by operators for maintenance, so they know what to maintain these motors, and it's got to be resettable in case they change a motor. So now let's look at a different system. It's not really a water-cooled system, but it is a different system. It doesn't fit in the other air handler modes. So radiant heating and cooling. So radiant heating is where we have circuits in a slab, and we take hot water and heat the pad up, and during unoccupied mode, so when it's occupied, the slab radiates heat. That's why it's called radiant heating into the space. And we also have now something called radiant cooling, which would do the same thing, and the only difference is the cooling water cannot be below dew point, or else it condenses water in the slab. So other than that, it's the same thing. Coolest down at night, daytime it absorbs. Instead of the radiation going off of it, the radiation is going into it. Very comfortable, it works very good. So the typical control sequence, The system shall be enabled, disabled based upon an occupancy schedule. System pumps. Start the lead zone system pump 12 hours prior to occupancy when in the occupied mode, so that the slab will be at the temperature when in the unoccupied mode. Slab will be at temperature set point prior to occupancy. If after 5 minutes the zone hot water pump status indicates no flow, then it's on the pump failure. Heating control. During the charge period for heating, run until the slab raises to 78 degrees set point or occupancy occurs. During occupancy, start the zone pump if the room temperature is less than 2 degrees below set point for more than 5 minutes. Run until the room temperature is 2 degrees above set point for more than 5 minutes. So heating is pretty simple. We try to charge it ahead of time, and then if it gets cold during operation, we turn it back on. No big deal. Cooling control. During the charge period for cooling, run until the slab temperature reaches 72 set point or occupancy occurs. During occupancy, start the zone pump if the room temperature rises above set point by more than 2 degrees for more than 5 minutes. Run until the room temperature is at set point for more than 5 minutes. Every 2 minutes, calculate the room dew point temperature from the room temperature and humidity sensor. Reset the zone chill water supply temperature set point to the dew point temperature plus 1 degree. Reset range should be limited to 55 to 68. So basically what's happening here is we have a temperature loop up here that takes cold water, then warms it up with return water, so we're always above dew point. We don't want to have any water on the floor, so we do that. Now this can also work where these zones are in walls or in the ceiling. They don't have to be in the floor. Same with this one, but normally, traditionally been on the floor because that's where the mass is. These are a mass cooling and mass heating system. They're very, very effective. They're very comfortable, and they're very energy efficient because of the mass. Monitor points, monitor all temperature and humidity sensors. If the zone hot water supply temperature is above or below set point for more than 5 degrees for 15 minutes, into level 3 trouble alarm. If the chill water supply temperature above or below set point for 5 degrees for more than 15 minutes, or below set point for more than 1 degree for more, it's in a level 3 trouble alarm. Alarm all equipment run failures, level 2 alarm. Data train the hot water supply and hot water return and chill water supply and chill water return temperature continuously with an interval of 15 minutes. Data train the room temperature and humidity continuously with an interval of 15 minutes. Data log runtime of motors and equipment, resettable by the operators for maintenance. These are real simple systems, but they work really, really well. So now we'll look at another system, which is a hydronic heat reclaim. And we use these in air systems where we have a whole lot of outside air or a high changeover outside air, and we want to take the energy out of the exhaust air and move it back into the outside air. So we recapture some of that energy, whether it's heating or cooling. So these are the systems that have a big coil, and this is a water circuit with a pump that runs the water between these systems. And it takes the energy from the hot coil and moves it to the cold coil, whatever they are. If you're in cooling mode, then it takes the cold air and the cold water, it cools the water and runs it over and cools the outside intake air. So it's vice versa. Depends on which one's higher or colder. Points are pretty simple. P1 stops this pump. Digital inputs, the pump status. Analog temperatures, outside air, entering air. So you put a outside air, entering air temperature, outside air, leaving temperature. And then we put an exhaust air, entering air temperature, and exhaust leaving temperature. So if this is the cooling coil, heating coil, hot coil, cold coil, so it depends on what these are. Let's say this is the outside air, and it's winter time to bring a cold outside air. So we take the heat out of the exhaust, and we pump it into the outside air to heat up the outside air. If it's the other way around, and this is the outside air control, and the exhaust is cold, then we want to take the heat out of the outside air and put it into the exhaust and exhaust it out the building. So that's the two ways we do that, but it works either way, either direction. Typical control sequence schedule. Again, the system shall be enabled, disabled based upon an occupancy schedule. System pump, start the pump, run around pump when in the occupied mode, and the differential temperature between the outside entering temperature and the exhaust entering temperature is greater than 8 degrees for more than 5 minutes in either direction. If the differential temperature drops to less than 3 degrees, so it's greater than 8 degrees Then we start it. If it's less than 3 degrees, we turn it off for more than 5 minutes. Stop the system pump. Once the system pump starts and flow is not confirmed within 5 minutes, stop the pump and send a pump failure alarm. During occupied scheduled times, the system pump shall be in the unoccupied time, the pump should be disabled. There's no reason to do this during unoccupied times. So monitor all temperature sensors on the graphic screen. Alarm system pump, run failure, level 2 alarm. Could be a level 2 alarm. Data trend outside air entering and leaving air cool temperature continuously during occupied scheduled times with an interval of 15 minutes. Data trends the exhaust air entering and leaving coil temperature continuously during an occupied scheduled time for an interval of 15 minutes. And the operator will use these to see if the sequence is actually working right. You can watch it and say, well, it's greater than 8 degrees. Differentially, it should be working. Data log runtime of the system pump, resettable by operators for maintenance. And that's pretty well for these simple sequences of water-cooled package equipment. So I hope that was helpful and kind of get you started on how to think about these sequences for the ones to come, which are more complicated, much more complicated. So appreciate you being here. Thanks a lot for watching. Have a great day, and I'll catch you on the next one. Thank you.